Hey everyone, so today we'll be solving a LeetCode hard problem, make array strictly increasing. So the problem states that we are given two integer arrays, AR1 and AR2. Now we need to return the minimum number of operations we need to make such that the ARR1 becomes strictly increasing. Okay, and how we'll be making ARR1 strictly increasing? We'll be performing some operations. So now in one operation, what we can do is we can choose two indices I and j from ARR1 and ARR2 and do the assignment. Means we assign the value ARR2 of j to ARR1 of I. Okay. Now after doing these operations multiple times, we need to return the minimum number of operations required such that we are able to make ARR1 strictly increasing. Okay, and we are given like the length can go up to 2000 only. So for example, if we have this as the input, so we know that this array is not strictly increasing because 1 5, then we have 3. Okay, so maybe we need to swap this 5 out. So we need to swap this 5 out such that we form a, means 1 is here and 3 is here, such that we form a strictly increasing sequence. So what value we can swap here? So suppose we assign air of 2 equals to 2 to this value. Okay. Hence the new sequence will become 1, 2, 3, 6 and 7. And which will be strictly increasing, and the number of swaps that we performed here is 1, which is the most optimal one here. Let's try another input. So we have 1, 5, 3, 6, 7 again, and we have 4, 3, 1 here again now this time. So now we do not have a 2 to put here. Okay, so now what we can do? We need to like make it strictly increasing. So we will not alter this one because this is like the minimum value we have in means combined values together. So this one will fix, be sure. Now we can either put like 3 here or 4 here. Like both of these choices are available. So which one is most efficient to try to like put a value which is greater than the previous element but as small as possible so that the further values can be like easily make greater than this. If we had chosen 4, then maybe we cannot make like 3 or something which will be greater than 4. Okay, so we definitely need a larger value to make this strictly increasing compared to the case of 3. So we'll definitely swap this 3 to this position. So we'll get 3. Now the sequence will become 1, 3, 3, 6, 7. Okay, and it is the same. It is sure like we can use multiple means the same value of from j multiple times. So we can assign means multiple values, multiple same values from the given AR2 to the AR1. But that will obviously never be the case because we want to make it strictly increasing only. So if we assign a value x here, then we will not be assigning any value x in anywhere because that will create a slope like this. So that will not be feasible. Okay, since we'll only be using any value from AR2 at most once only. So now we have this index. There is 1, 3, 3, 6, 7. Now we need to make this strictly increasing. So this 3 is altering our chance. So what you can do is we can either swap it with 1. No, it will not be good. 3, not good. 4, yeah, it is good. So this array will become 1, 3, 4, 6, 7. And now we see that this is an strictly increasing array and hence the number of swaps that we performed were 2. Hence the optimal output here is 2. Let's try for another input. So again we have the same array 1, 5, 3, 6, 7. We initially made the sequence 1, 3, 4, 6, 7. So again we push 3 here. So we have 1, 3, 3, 6, 7. Now we need to swap this 3 with either 4 or 5. But we do not have any 4 or 5, right? We only have a 6 or a 1. Means 1 will decrease and 6 will increase it a lot because this 6 will become equal now. So hence there is no possible ways of swapping such that we can make this ARR1 as increasing. So in this case we will be returning -1 here. So now like what means analysis can be made based on the test cases and the problem statement here. So obviously like we know that at each index means each index in AR1 we have like either a choice of keeping this element as the same or swapping it with some element from AR2, right? So means each element in index, each element in ARR1, each element in ARR1 has two choices. Either keep it same, or swap it. Okay. So these are like the two means choices for each element in ARR1. From that, like if we try to see like derive what means what algorithm can be used to solve this problem, so maybe based on the choices that we have, maybe like dynamic programming can be applied here. Maybe we are just like trying to analyze the problem statement current. Now how can we like apply DP here is we first need to identify the states which will be means representing the transitions that we need. So this means problem is tagged as hard, but it is like means super hard because thinking about the DP state here and means it is not pretty standard. Means generally like the DP that we play with is based on the indexes, or means the states that will be changing are mostly indexes and so on, right? But here thinking about what will be storing in the DP and how these states will be changing is like pretty difficult. So even if you like you already knew that this is a DP problem, but still like thinking about the states is real tough. So like let's try to analyze how we'll be like able to how will we try to maintain the DP states. So we need to know like if we are at a particular index I, and to calculate whether we can like the number of swaps operations required to make the index means array till AR1 from 0 till I as strictly increasing, we need to like what do we need to know? So means we would have already calculated the answer till I minus 1, right? So now for this index means element at index I, we have the choices as keep this element or swap it. Now when we'll be keeping this element, we'll only be keeping this element when this ARR1 of I will be greater than ARR1 of I minus 1. And now this ARR1 of I minus 1 is not fixed, means this priv element will not be aware of it because it will be changing based on like whether we have performed swap on the previous element or keep it same, right? So this priv element will be changing. So maybe we can think of the DP state in the form of DP of I and the priv element that we had, means that we chosen at the index I minus 1. Okay, maybe. And then it will store the minimum number of operations required, minimum operations. But as we know, like this priv will be a element means value of the array, and the value of array can go up to 1 in 9. Hence like this will obviously give us Emily here because it will be n into 1 in 9, which will obviously be not be feasible here. Hence this we cannot use. So like instead of maybe storing the priv element, we store the index which is from which it is coming from. So now again for index it can have multiple values because for DP of I from 0 to I minus 1 it can have the value of error of 1 of I minus 1, or it may be swapped value from any index from 0 till m minus 1 from error 2, right? So again like storing the index as part of the DP state will not be feasible because it can be I minus 1 or any element from 0 till m minus 1, and we will not be sure of which element will be swapping, right? Because this, so obviously like this will also be means not be accountable later because we suppose we use this I minus 1. Okay, so now suppose this represents value 3. So what if we have an index 3 in the ARR2 area as well? Yeah, so then how will we be able to differentiate whether this 3 is from ARR1 or ARR2, right? We'll not be able to differentiate this. Hence like using this index thing of from where the priv element came will also not be feasible here. But we are sure that we definitely need this means information about the previous element that we had at the previous means index. then only we'll be able to know whether to swap the means if the ARR of 1 of I is less than pref, then only we'll be swapping it. We will know that we definitely need to swap the current element, right? So we need to know whether means the information about the pref element, and we are seeing that we cannot store it as part of our state, because if we keep it pref the element keep it the pref element as part of a state, then it will go till 1e9, and if we try to keep the indexes, then the indexes can be same from ARR1 or ARR2, this I minus 1. If this value, suppose it was 3, it can still be found in ARR2. So then we need to like, how will identify whether this 3 came from ARR1 or ARR2? So this is also not feasible. So now what do we do now? So we know that this pref value needs to be stored. So what if we store this pref value in DP itself? Means DP stores this pref value. Okay, so this is the means the point where this problem means is very different from the standard DP problems. Here we needed to minimize the number of operations, but our DP will not be means representing the DP value will not be storing the minimum number of operations required. Instead, it will be storing this pref value, means for DP of I, it will be storing the number means the pref element that will be using, pref element used at I minus 1. Okay, this is what DP of I will represent. And now since this pref element can means account at different possibilities, and we also need to minimize the number of operations. So what the second state we can make is the number of operations, number of swaps made to get that pref. Okay, number of swaps made to get that pref. Hence, the DP of I comma j to make the all the sub problems, means to account all the sub problems possible, DP of ij will be nothing but the element, the minimum possible, because we will be assigning elements in such a way that this element is as minimum as possible and still strictly increasing, so that we can assign the next element easily. Okay, so the minimum possible element at index I with j swaps performed. Okay, so this is where means the identification of DP state is very difficult, because here in DP state we are not storing the result that we are looking for, because we need to minimize the number of operations, but in our DP we are not storing it. Why we are not storing it? Because this pref information that we needed was very important, and we are not able to keep it as a part of our state. Hence we moved on to what if instead of being part of a state, we store it as a part of the result itself, and then try to from this then try to reverse engineer, or how means what can be the changing state here. And we observed like the number of swaps performed can definitely directly influence the element present at that index, because if the swaps performed are 0, then the elements will be as in the same order as ARR1. Okay, but if swaps performed are 1, then this element will be changing, right? So we identified like based on the number of swaps that we have performed till now, this means the minimum possible element at index I will be changing, and this is the minimum possible element is such that the array from 0 till I is strictly increasing. Okay, so this is the DP state that we will be using. So once like the state is clear, now the aim is to identify the means the base case. Identify the base case. Okay, so what will be by base case here? So we have the DP of suppose n cross n, because the n cross n plus 1, because the maximum number of swaps that we can perform in an array of n, length n will be n. Okay, so this index will be going from 0 till n minus 1, and swaps will be going from 0 till n. Hence we need a DP state of n cross n plus 1. So what will the dp of means how will be defining the base case here? So obviously, like if we are at a particular index I, then the maximum number of swaps that we can perform till that array is less than equals to I plus 1, right? Because if we are at index 0, then the maximum number of swaps that we can perform is less than equals to 1. Means either we can swap this element or not. If we have two elements, then the maximum number of swaps will be I plus 1, means the number of elements that we have. Hence this swaps will be less than equals to I plus 1. So definitely for values which are greater than, means swaps greater than I, it will never be possible. So to represent like never possible, we can store like a very, since we are requiring the minimum possible element at index I, so we can store a very large value so that we do not account it. So maybe store int max in this case. Okay. So now this will means looking in the direction, we can like try to think of the base case here. So for dp of 0, we need to identify for dp of 0, swaps can be 0 or 1 because it should be less than equals to I plus 1. So now we need to find dp of 0 0. So dp of 0 0 means we performed 0 swaps till 0th index. So hence the minimum element will be, since we have ARR1 and ARR2. Okay. Now suppose we have the ARR1 and we have not performed any swaps. That means this first element will remain intact only. Hence this will only be the minimum element that we'll be using. So this will be simply ARR1 of 0. Okay. And what will be dp of 0 1? This means like we have performed one swap operation, right? Means we have swapped this first element with some element from ARR2. Now with which element will be performing a swap operation of this first element? Obviously the minimum element from AR2, right? So that the slope means this slope starts from the bottommost point only, so that it is possible to still make it strictly increasing, right? So we'll be swapping this element with the minimum possible element from ARR2. Hence if we like initially sort the ARR2, because we will be able to, means we are allowed to use the elements from AR2 in any way possible. So what we can are allowed to swap it so that we are means easily able to find out the minimum element required. Okay. So it will be simply what? ARR2 of 0. Because we will be performing swap in the most possible way, means most optimal way, and since we need to minimize the element stored at index I, so we'll perform the swap with the minimum element present in ARR2, which is ARR2 of 0 after we sort the ARR2. Okay. So this is the base case. Now what about the transitions? What about the transitions? So I hope the base case is clear. For dp of 0 0, it is this, dp of 0 1 is this, and for any value like dp of 0 and any value greater than 1, it will be what? We will be storing int max. Because obviously we will not be performing like multiple swap operations, because we will not, like if we have the first element, then we assign it with ARR2 of 1, then if we assign it with ARR2 of 0, means this will obviously not be feasible because we want to minimize the number of operations, right? So this is obviously not optimal to like assign this ARR2 of 0 value by first assigning ARR2 of 1 and then assigning ARR2 of 0, using means two swap operations to make this value ARR2 of 0. Alright. So hence for any value, means number of swaps greater than 1, will be storing the result as int max. This represents that it is like using greater than 1 swap operations is obviously not feasible here. Okay. So now the next step is to identify the transitions. So what were the choices that we had? The choices were like either to swap or not to swap, or not to swap. Okay. These were the choices that we had. So let's see the case of swap. Okay. We perform a swap operation at index j. So when we perform a swap operation at index j, that means this j would have increased by some value, right? So initially, suppose if we perform a swap at this in particular index, we'll perform a swap in the most optimal way until dp of I minus 1 will have performed, means since a swap operation is being performed at this index, so we'll be definitely be looking at the value, means till dp of, means till index minus I minus 1, we have performed j minus 1 swap operations, right? Because we are performing a swap operation at the ith index. Now how will be like performing the swap operation? So we know like this will represent the min prev element at index I minus 1, right? Means this dp of I minus 1 comma j minus 1 will be representing the previous element that will be storing in ARR1 with j minus 1 swaps. Hence, if we are allowed to perform a swap, that means if we have the current value as ARR1 of I, so we'll be swapping it with some element in ARR2, which is like the, we'll be performing swap such that it is just greater than its prevalent, right? That means it is, we'll update it in such a way. So for example, if we had like 1 3 and we have an element 2 here, so this was the prev element which was stored in dp of I minus 1 comma j minus 1. Now we need to update this, means we are allowed to swap this 3 with some value from this. So here suppose we had 2 4 1 6 here. Okay, so now how will be performing the swap operation? So we will be swapping this with such a value such that it is the smallest value which is greater than this value, this prev value, right? So that means smallest value greater than what? This dp of I minus 1 comma j minus 1. And what is this value? It is simply upper bound of dp of I minus 1 comma j minus 1 in what? ARR2, because that's why we have like sorted the ARR2 initially as well. So in this case, what will the transition be? It will simply be dp of ij. If we perform the swap at this step, it will simply be what? dp of I minus 1, means it will only be updated if dp of I minus 1 comma j minus 1. So if like the upper bound that we find exists in this case, so if like upper bound exists, upper bound, so suppose auto it we find auto it equals to upper bound in ARR2 of what? dp of I minus 1 comma j minus 1. Okay, so if this upper bound, means this it is not equals to ARR2.end, okay, that means we'll be able to update this dp of ij with the value that this it will be representing, right? So hence the dp of ij will be nothing but this star it, okay, because this will be the minimum value that will be storing at dp of ij. So I hope the logic here is clear, because at each step, and since we have like initialized the dp with such a way that initially it was int max, so we can either take it minimum or store the star it value here, right? So this was the case, in this case where if, means this upper bound existed and it was possible, means the prep value was such that the prep value existed, means dp of I minus 1 comma j minus 1 is not equals to int max, obviously. So this will obviously be seen by the upper bound, because there will not exist any upper bound, and this means j should be greater than 1, then only this j minus 1 will be existing. Okay, so this will be the case of the swap transition. Now what about we perform no swap at index I? Okay, we had the choices. So I hope like the swap operation is clear and the swap transition is also clear. Like how we'll be finding out the upper bound and updating that upper bound's value with, means at the current dp. Now if you do not perform any swap, so this will only be feasible if means it will only be feasible if the value that we have at ARR1 of I and the value that we have at dp of I minus 1, and since we are not performing any swaps, means the number of swaps will remain the same only. Okay, so till index minus 1, with j swaps will have some min prev element. Okay, this will be denoting that prev element. So we need the error of 1 of I should be greater than this value, then only it will be strictly increasing, right? So if this value is greater than, means if this condition is satisfied, then we'll be updating dp of ij with simply error 1 of I. Okay, so this is the case of performing no swap operations. So once we'll have filled the entire dp array in following this form, how we'll be calculating the final answer? Means the next step is to identify how we'll be calculating the final answer, because main goal was not to identify the minimum prev element which will be storing at the last or at the start, or means this was not the problem. The problem was to identify the minimum number of operations. So we need to identify this, not the minimum prev element. So how will we be finding it? So since we will definitely process means till the n minus 1th index the dp. So in the dp of n minus 1, for 0 swaps, for 1 swaps, for 2 swaps, and so on, we need to see the first value, which is, suppose it was int max, then this was also int max. Suppose this value is not equal to int max, it was 4. So that means we are able to allocate this 4 using this means these many operations. And if we are able to allocate 4, this means we have definitely been able to get an increasing sequence, strictly increasing sequence. Hence, this means that first j, which is not, means first j in dp of n minus 1, such that dp of n minus 1 and j is not equals to int max. That means that is the first value, and that will be the number of operations, minimum number of operations required, because after that all the values will be of the form of these one, means something of any of the order, such that it maintains a strictly increasing sequence. So this is the approach of the problem. The idea, I hope, like how we moved on to analyzing why standard dp states will not work here was clear, like why we are not storing this prev as part of our dp state was clear. And then since this information was very crucial, so we moved it as part of the dp result only, and then perform the swaps. Means at each index we had two choices of like performing a swap or not performing a swap. So we executed these two swap means choices, and see like how we'll be performing these swaps in the most optimal way, which is obviously to take the upper bound of the previous element, so that the next element is just greater than the previous element. And we'll follow this order to build a strictly increasing sequence, so that we are able to satisfy the condition for all the elements. Okay, or we do not perform any swap at each step. So this will be the case where the prev element is not already, means it exists, means it is not already int max, and this value is like simply greater than error of 105. And in this manner we will be able to means fill the dp states. And once we have filled it, how do we identify the minimum number of operations required? So it will be identifying the first index j, which such that dp of n minus 1 comma j is not equals to int max. So what will the time complexity of this approach? It will be simply, since the dp states will be filling, so it will have n and n plus 1, so it will be n square, and inside the filling of the dp state we need to find this upper bound, right? And upper bound we will be finding in the error 2. So suppose it has length m, so it will be n square into log m. Okay, so this will be the time complexity of this problem, and which is fairly acceptable, because n can go up to 2000 only. So it will be 4 into 1 is 6, then you have 6 into log of, means log 2 of 2000, which is like 2 to the power 10 to the power 11. So 11 means 44 into 10 to the power 6, which is simply approximately 10 to the power 7. So hence this will be fairly enough and means satisfiable for this problem. So let's see the code here as well, and like identify how we'll be implementing it. We'll be discussing the same implementation that we did. So initially we'll just be simply sorting the second array, so that at each step we are able to find out the just greater element from the prevalent. Okay, we state means initialize the DP state with of size n and n plus 1 because we can perform swaps less than equals to n, and we initialize it with int max so that we know whether it is possible to means whether it is optimal to perform that many swaps operations or not. Okay, then the base case here, this is the base case, this is the base case, this is the case where the DP of 0 0 means we do not perform the swaps, hence the first element remains the same, and this is the case where we perform a swap. So we can only perform a swap if error2 means size exists. So let's see whether size, yeah, so it is already greater than 0, so this check is also not needed because it is mentioned in the constraints only. So DP of 0 1 means we have performed one swap operation, so we'll be definitely be picking up the minimum element from this error2. So we'll update it with error2 of 0. Now we'll be filling the DP states. So how we'll be filling it? For each index from 1 to n minus 1, and the number of swaps performed till I will be less than equals to I plus 1, right? So hence we'll move j till this index, till this possibility is only, because performing these many swaps only is optimal, because otherwise it will be definitely be returning into redundant swaps, which you do not want. Now the transitions will be, the first transition is to keep the error1 of I same, means we'll perform no swaps. Hence till previous state DP of I minus 1, we should have the same number of swaps. So we'll look at DP of I minus 1 comma j, and it should be, means error of 1 of I should be greater than this value. This means it should not be int max, then only it will be greater. So you can simply like avoid this as well, because it will only be executed if this value is greater than DP of I minus 1 comma j, and it will never be greater than int max. So we'll update DP of ij with the minimum of DP of ij comma error of 1 of I. Okay, and the next transition that we need to do is swap the current element. So we'll be swapping it with the lower bound of DP of I minus 1 comma j minus 1. Okay, and if the lower means if the upper bound exists, means the first value greater than DP of I minus 1 comma j minus 1. So if this value exists, then we'll be updating DP of ij with this value, and then we'll be, means in the end we'll find out the answer for the first jth column, which is not int max, and that will be the result. So we'll simply return it, and if we have not found any such j, then we'll simply be returning minus 1 in this case. So this is like the n square log m approach for this problem. Let's try to submit the code as well here, or like I will show you my submissions. So yeah, currently internet is not working, but it will be feasible only. Okay, so this is like pretty much it for this problem. I hope like you will now be able to understand like how we will be manipulating the DP states and to like satisfy our requirements for different scenarios. And this is like super hard, because like storing these, thinking about the DP states and what the value DP will be representing was like super difficult here. So I hope like all your doubts are cleared, and if they are, please like the video, and if you have any doubts, feel free to comment down and I will be happy to help. Thank you for watching.